Hello everyone and welcome to my channel. Today we are talking about the empirical mode decomposition, in short EMD, which is a decomposition method that I have been using a lot over the past 2 years for different applications in the field of fluid dynamics, and I thought it would be nice to share some fundamentals with you and motivate you to try this algorithm on your own data. Before we get into the details, I briefly like to explain the different terms of the name of the method because I think it already gives us some hints what to expect from the method. A decomposition is a separation of your signal into different components, and you usually do this in data analysis if you want to extract some information from your data that you cannot obtain when you consider the data as a whole. So you decompose it. You analyze the newly obtained components to gain new insight into the features inherent to your data. Of course, there are several methods to perform such a decomposition, and the EMD is just one of them. A decomposition usually includes a coordinate transformation, meaning that you take your data and you project it onto a new basis system, which allows you to decompose it in a prescribed manner. Different decomposition methods generally differ in the used basis system, and we will briefly talk about some of them in a few minutes. If you're not familiar with data analysis, the term mode sounds maybe kind of abstract, but it is essentially just another name for the components that you obtain from the decomposition. So a mode is just a portion of your complete signal. And depending on the decomposition method you use, a mode can look quite different. As you might have already guessed, the term empirical is the most important one to tell us something about the method. In contrast to most other decomposition methods, the EMD is empirical, which means that it is not based on a prescribed basis system, but the data itself dictates the decomposition. As I said earlier, a basis system kind of builds the foundation for your decomposition, and having an adaptive basis system is a big advantage when it comes to determining physically meaningful modes from your data. The majority of state-of-the-art decomposition methods builds on a well-defined mathematical basis, but this does not necessarily mean that the modes you extract by these methods contain physically relevant features of your data. In contrast, the EMD is lacking a concise mathematical foundation, but it compensates that with some really helpful characteristics that we will discuss later in this video. Okay, now that we gained some information about the EMD and have an idea what to expect from this method, we will briefly check why using an EMD might be valuable for your own application. Usually the main goal in data decomposition is to obtain components of your data that are more effective than the complete data in providing novel insights into some hidden features contained in your data. And there are several methods to do that. I will briefly address a few of them that I find really important, although I might be biased by my field of research, which is fluid dynamics. If you'd like me to do a dedicated video in which I compare the different methods in detail and give some advice how to decide which method is most suited for your specific problem, then let me know in the comments below. Okay, now the most important method, the one I guess is used the most, is the Fourier Transform. It is a coordinate transformation which projects your data onto an orthogonal basis system with sines and cosines. So it covers all frequencies that could be contained in your data and assigns weights depending on the importance of each frequency for the system that is represented by your data. These weights are the amplitudes of your sines and cosines. But in a strict sense, the Fourier transform is only valid for linear and for stationary data. But since nearly all of our real-world data is nonlinear and non-stationary, we can only obtain an approximate result using the Fourier transform for this kind of data. The Wavelet Transform is an extension of the Fourier transform, and it additionally includes temporal information. So instead of only telling you which frequencies are important to your system, it also shows you at which time instances they occur. And later in this video, we will take a look at some example spectra in the frequency time domain obtained by the Wavelet Transform and compare them to spectra based on the EMD. The singular value decomposition, in short SVD, builds the basis for the principal component analysis and the proper orthogonal decomposition. These methods do essentially the same decomposition, they were just derived from different fields of study. So the orthogonal basis system of the SVD is based on the direction of highest covariance in your data. It's a generalization of the Fourier Transform, and it is data-driven, since the first axis points in the direction of highest covariance, the second axis in the direction of second to highest covariance, and so forth. And the resulting modes are consequently ordered hierarchically with decreasing importance to the system. The dynamical mode decomposition is also based on the SVD. It provides a dynamical system which represents the temporal evolution of the modes you obtained by the SVD. So now that we are hopefully all on the same page, we can take a look at the main features of the EMD and how they distinguish from the other methods I just talked about. So the most important characteristic of the EMD is its ability to process nonlinear and non-stationary data. We already noticed that most of our real-world data, whether we acquire the data from experiments or from simulations, is nonlinear and non-stationary. So it is a significant advantage of the EMD compared to the other decomposition methods that it is able to cope with such data. This property is achieved by using an adaptive basis system. We saw earlier that other methods, like the Fourier Transform, prescribe a specific basis system. However, the basis system used by the EMD is dictated by the data itself, and so the modes are adaptively biased towards locally dominant frequencies when we use the time-dependent signal. And if we use spatial data, the modes are biased towards dominant scales. This allows the EMD to extract physically meaningful modes, which is another very useful property of this method. Since we decompose our data to obtain components that should help us in analyzing the features of the data, it is of utter importance that these components reflect physical features. Otherwise, our analysis might result in misleading findings. And although all the other decomposition methods usually produce mathematically meaningful modes, their physical significance is not necessarily given, and we have to be very careful with the conclusions we draw from such modes. I hope you now have a good impression of why you should give this decomposition method a try. Next, we will see which type of data we can use for the EMD. To keep it easy and understandable in the first place, we will start with a one-dimensional univariate EMD. This is the very first version of the EMD that was introduced in 1998 by Huang and co-workers. I have put the corresponding paper on this slide, and I highly encourage you to take a look at this paper when you decide to use the EMD on your own data. Don't be overwhelmed by the number of pages. The paper is written very well, and it contains a lot of examples, so you will get through it faster than you think. This publication was already cited more than 20,000 times, which is quite impressive and shows how many researchers already applied the method to their data. It is used in a variety of applications, and at the end of this video we will have a look at a few examples. But let's get back to the data we are about to apply the EMD on. We're using a one-dimensional univariate signal, and I have plotted one example for this type of data on the left. In this context, one-dimensional means that our data has only one direction. This can be the temporal domain, as in our case, or it can be one direction within the spatial domain. Univariate or single variate means that the signal has only one component, so it's a vector. For example, if we measure the velocity of a fluid flow at a single position within the flow over time, we obtain 3 velocity components, so one component for each direction of our coordinate system. However, for this version of the EMD, we would only consider one of these components. There are extended EMD algorithms that decompose multidimensional and multivariate data, and I will discuss some of them in upcoming videos. But for now, throughout the following explanation of the working principle of the EMD, we will use the time-dependent signal plotted on the left, and we call this signal f of t. It has small and large-scale fluctuations, which means that it contains different frequencies. And it also has positive and negative values. At a first glance, we cannot be sure if it has zero mean. However, the EMD can also handle non-zero data, so this doesn't matter at this point. Before we take a closer look at how the algorithm works, I'd like to show you the outcome of the decomposition. So just that we know what to expect from the method. The modes produced by the EMD are called intrinsic mode functions, in short IMFs. For the signal that I showed you previously, our signal f of t, the resulting IMFs are plotted in this figure. I know it looks quite confusing at a first glance, but let's take a look at the modes together. The first IMF, which we call IMF subscript 1, is plotted in light blue. It obviously contains the highest frequencies since it fluctuates massively in a short period of time. Considering the next mode, IMF subscript 2, which is shown in orange or red, the fluctuations are very much reduced. And we see that with increasing mode number, the frequencies contained in the modes reduce even more. And this is one of the main characteristics of the IMFs. They are always ordered from highest to lowest frequency content, or, if we have spatial data, from smallest to largest scales. And later we will also see why this is the case. You might have also realized that the IMFs fluctuate around zero. This is also enforced by the EMD. The only non-zero mean component is the remaining residual, which we have abbreviated as res. If your signal contains a large-scale trend or it has just non-zero mean, this is found in the residual. The decomposition by the EMD is complete, meaning that the sum of all modes and the residual resemble the original data. So principally, we could now start to analyze all these components with respect to the information we want to extract from the data. However, I think before we start such an analysis, we should understand how the IMFs are produced. So let's get started. Here you see again our signal f of t, and you also see that I have marked all local maxima and minima, since finding these extrema of the signal is the first step of the algorithm. This step is rooted in the fact that the main assumption of the EMD is that the characteristic time scale of our signal is defined by the time lapse between the signal's extrema. So if we want to extract modal representations of the signal that contain specific characteristic temporal features of the data, we have to rely on these extrema. Next, we fit an envelope through all maxima, which we often refer to as the upper envelope, and we also fit another envelope through all minima and call this envelope the lower envelope. The fitting is usually done by cubic spline functions, but you could essentially use any function you like. You just have to ensure that both envelopes cover all data in between them. Next, we determine the mean envelope, which we obtain from the mean of the upper and lower envelope at each point in time. You see this envelope in green color in the plot. Finally, we determine the residual, which is obtained by subtracting this mean envelope from the original signal f of t. The residual is shown in violet in the figure, and you can see that it seems to have zero mean. So it could already be our first IMF. To decide that, we use a stopping criterion. In the original version of the EMD, the stopping criterion is essentially a standard deviation, which considers the squared difference between the original signal f of t and the newly obtained residual normalized by the squared signal f of t. The values are summed over all time steps t, and the resulting single outcome is compared to a threshold value, which we here call epsilon. We won't go into detail about this threshold, but usually epsilon is in the range of 0.2 to 0.3. Usually, the first residual we obtain does not possess the characteristics of an IMF, and the stopping criterion is not satisfied. If we inspect the massive difference of our signal f of t and the residual, we can imagine that the stopping criterion would not be fulfilled for this residual. And this is because the extrema fitting often produces over and undershoots, and new extrema are generated, which have to be eliminated before we can call this residual an IMF. Of special importance are so-called riding waves, which means that a minimum is larger than 0 or a maximum has a value smaller than 0. Since we want to determine a mode that has a local zero mean, these riding waves have to be removed through several iterations. In addition, the wave profile is made more symmetric through these iterations. However, this can artificially damp amplitude modulations that are inherent to the data. So the stopping criterion has to be chosen with care to find a compromise between these tendencies. So if the stopping criterion is not satisfied, so this expression here is false, we repeat the process with the residual until the stopping criterion is fulfilled. Let's get through this procedure once again to make sure that you get all the necessary steps by heart. Again, we determine the extrema of our signal. You see here that we are using the residual that was the outcome of the first iteration. Then we fit one envelope through the maxima and one envelope through the minima. The mean of these envelopes is now again shown in green in the figure, and we subtract it from the residual to obtain a novel residual, which we call res subscript 2. Both residuals, the violet curve is the first residual and the light blue curve is the second residual. They look quite similar, and we can assume that the stopping criterion would now be fulfilled if it's not very, very strict. So the expression is now true, so what do we do next? We call this new residual our first IMF, and we subtract it from the original signal f of t to obtain an updated version of our signal f of t. In this figure, you see the original signal f of t in blue, the residual, which is now the first IMF, in light blue, and the updated signal f of t in black. As you can see, the updated signal appears to be kind of a low-pass filtered version of our original signal. And this is because the first IMF contains the highest frequencies of the data. Let's see why this is the case. So the smallest time scales, that means the highest frequencies, we can resolve are dictated by the time lapse between successive extrema of the original signal. Since we derived the first IMF directly from the extrema of the original signal, it contains the smallest time scales. Now that we would repeat the same process we did earlier with f of t, but now using the updated version of f of t to obtain the second IMF, we can see that the second IMF must contain larger timescales as the first IMF, since we already filtered out all high-frequency components. And this is why the modes extracted by the EMD are always ordered from high to low frequency content, and why this iterative process is also called a sifting process, since, like in sifting, you first extract the smallest parts of your data or of the material, and step by step you increase the size of the extracted components. Okay, let's get back to our sifting procedure. After obtaining the first IMF, we would repeat the iterative process with the updated signal f of t to obtain the second IMF. Once we have obtained the second IMF, we would subtract it from the updated signal f of t, so we updated it once again, and proceed the process with the updated signal to obtain the third IMF, and so forth. So you see, the essence of the EMD is an iterative process that is repeated in two aspects. First, it is processed with a pseudo IMF, which we call the residual, until the correct IMF is determined. And second, it is walked through with the updated signal, so the preceding signal f of t minus the IMF, to obtain the subsequent IMF. The question might arise when we stop the decomposition. And we usually stop when the residual is a monotonic function from which we cannot extract any extrema. And now we see the result that I have already shown you earlier. All the IMFs and the remaining residual we obtained by decomposing our signal f of t by the EMD. In total, we obtained 5 IMFs and 1 residual. I hope that you now have a good intuition of how these components are obtained and what the whole decomposition is based on. Let's take a look at some examples. So the first example I've chosen is included in the first EMD paper by Huang and co-workers. On the left, you see some ocean wave data acquired at a tidal station. It displays the variation of the ocean's surface as a function of time. The data looks quite chaotic and random, and we will not be able to extract any meaningful information out of it, at least if we are not familiar with ocean wave data. In the past, such data would have been analyzed by the Fourier Transform, or rather the Wavelet Transform if we wanted to include the temporal information. However, Huang and his colleagues show in their paper how much more information we can extract from the signal if we use the EMD instead. And that is what we are looking at now. On the right, you see the IMFs extracted from the wave data. In total, we have 7 IMFs and 1 residual. The residual appears to represent the tidal variation. Fine, but what can we see from the other components? I am not an expert in the field of oceanography, and to be honest, I cannot interpret anything meaningful out of it. But I'm here to show you how powerful the EMD is, and this is something we can look at. So it is common to combine the EMD with a Hilbert spectral analysis for a complete analysis of the data. A significant advantage of the EMD is that the resulting modes have well-behaved Hilbert transforms, and so they can provide us with instantaneous frequency and amplitude values as a function of time. This means that we can look at an energy-frequency time distribution, which is usually referred to as the Hilbert spectrum or the Hilbert energy spectrum. If you're not familiar with the Hilbert transform and the Hilbert spectrum, and you'd like to do me a detailed video about this topic, then let me know. But for the moment, it is less important that you know how to calculate the Hilbert spectrum mathematically. Just look at this figure here, which shows the Hilbert spectrum of the IMFs obtained from the ocean wave data. The time steps are plotted on the x-axis, while the frequency values are plotted along the y-axis. The coloring indicates the energy associated with each combination of frequency and time. It's just the squared amplitude that we obtained by applying the Hilbert transform to the IMFs. you see that the ocean wave data behaves highly intermittent, so the frequency content varies strongly with time. And as I've already mentioned, this type of data would have been analyzed using the Wavelet Transform in the past. So the Wavelet Transform can also provide us with an energy frequency time distribution, and you see this distribution for the ocean wave data on the right. Compared to the Hilbert spectrum, the wavelet spectrum is more continuous. It has very different energy distributions, especially for the frequencies around 0.1 Hz, and it includes much higher frequencies. So where do these differences come from, and which spectrum is more physical? The rather continuous energy distribution across the whole field of possible frequencies and the smooth appearance of the wavelet spectrum actually point to drawback that arises from the Fourier basis. You hopefully remember that the Fourier transform uses a basis system of sines and cosines. So it must project the ocean data onto these orthogonal and periodic bases. But for highly non-stationary and non-periodic data like the ocean wave signal, this is quite challenging. So the Fourier transform must introduce additional harmonics that are not physically contained in the data, but serve the purpose of fitting the periodic functions to the non-periodic data. Not only does this introduce spurious frequencies that are not actually inherent to the data, but it also smears the energy content across more frequencies. This means that the frequencies that are actually contained in the data cannot be assigned to their correct physical energy. So we clearly see why the EMD is superior for applications like that. The EMD modes enable a profound analysis of data with highly localized and quickly varying features, since it gives a sharp identification of these features in time and frequency. The next example is a vibration signal from an automobile gearbox, which is used for localized gearbox fault diagnosis. You can get detailed information on this analysis in the paper by Leo and co-workers, which I put at the bottom for reference. The vibration signal you see on the left is collected from an automobile gearbox with an incipient tooth crack 1 minute before the tooth was actually broken. It shows the magnitude of vibration as a function of time. Like in our previous example, such data was commonly analyzed by the Wavelet Transform, and the authors show that the EMD in combination with the Hilbert spectrum is more efficient in detecting such faults prior to them causing actual damage. On the right, you see the IMFs of the vibration signal, and here on the left, we have the corresponding Hilbert spectrum. Again, we compare to the wavelet spectrum, which I have plotted on the right. But let's start by inspecting the Hilbert spectrum. The average time spacing between neighboring impulses is about 0.17 seconds, which is close to the rotation frequency of the damaged gear. The frequencies of the transients range from 0 to about 300 Hz, which clearly reveals the existence of a localized defect on one of the gears, if you know all the details about the experiment that you can get from the paper. So we see that the EMD very clearly reveals all the information we need to detect which component is about to get damaged. However, we see that these details are smoothed in the wavelet spectrum. In fact, you really have to know where to look at, because the higher frequencies dominate compared to the frequency range that is actually of importance for the current diagnosis. So we see that the EMD provides more distinct and explicit information about the fault, and is obviously the method that is more suited for this application. There's a variety of other examples in which the EMD outperforms other methods that have been used previously for these applications. So for example, EMD seems to be very helpful in denoising and analyzing ECG data, and here are just a few publications I found on this topic. but EMD was also successfully used in the fields of solar systems, geophysics, turbulent flows, and many more. So let's just do a quick recap of what we have learned today. A data decomposition separates a signal into components, which we call modes, to gain new insight into inherent features that we could not detect when we just used the complete data. We have seen that the EMD can easily outperform the Fourier and the Wavelet Transform, but it can also be superior to other decomposition methods that we have not covered in this video today. And this is mainly achieved by its ability to process nonlinear and non-stationary data, where other methods can usually just serve as linear approximations. In addition, the EMD produces physically meaningful modes and can precisely identify features in combination with the Hilbert transform. We have seen that events which are highly localized in time and frequency are very well resolved by the EMD. The IMFs produced by the EMD are obtained from an iterative process, and we have seen that this process includes one loop for determining a single IMF and another loop to extract all these IMFs. The frequency range inherent to the modes is based on the time lapse between successive extrema of the data, and the resulting modes are ordered from highest to lowest frequencies or smallest to largest scales. So I hope that you find this video informative and that I could give you a good impression of how powerful the EMD can be. And maybe you try this method on your own data and see if you can get some new information out of it. I wish you a wonderful day and hope to see you in the next video. Bye!